This is part 3 of 8086 assembly language programming, and we will see how we can write a program containing a procedure to compute the factorial. So before using procedures, there are certain things we need to know, like how we can pass parameters to the procedure. So stack is one method that can be used. So here the stack refers to the stack attached by the OS with this program while it is running. Okay, so the parameters that are required for the procedure to work, they are pushed into stack, okay, into the stack frame of the main program, so, or the main part of the program. So there will be a main part of the program which we'll call the procedure, right? So that main part's frame, stack frame, will hold the parameters initially. Now how will the procedure take it out? As usual, at the assembly language programming level, what the system expects us to behave is, when we enter into a procedure, we will open a separate stack frame for that procedure, which will hold its local variables or the push or pop within that procedure. Okay, so we will create a new frame for the procedure within the same stack, but we will use indirect addressing to get into the previous frame of the main part of the program, okay, and take out the parameters. So this is what we are going to do. Then another thing that you need to take care while writing a procedure in assembly programming language is, whenever you get inside a procedure, write code to manipulate something, whether mostly they will be registers, contents of registers. Before manipulation, you have to preserve them. Then after your work is done within the procedure, you have to restore them. The main reason is we have only a limited number of registers within a machine, and the main part of the program as well as your procedure will be sharing these registers or using the same registers. So when the procedure returns to the main part of the program, you expect the program to behave as it is supposed to be, right? It should not deviate from what it was doing earlier, like what it was doing before the procedure invocation was done. It should continue with what it was doing before the procedure invocation. So that state is actually kept in the register contents. So whichever contents, whichever registers you are going to manipulate within the procedure, you have to actually preserve them. So that preservation can be done by using the stack frame of the procedure that we created just now. Okay, you can push all the registers which you are going to use, and then after your use you can pop all the registers back to their original value. Then there is another rule regarding where should you keep your procedure. Okay, so procedure, just like another part of the program, is kept within the code segment. Okay, so it is not just like high level programming languages when the invocation only triggers the procedure. The placement of the code of the procedure can also accidentally trigger invocation, not invocation, working of the code within the procedure. Okay, so we will see how it has to be properly placed. So let's go through the code that we wish to run. Okay, so if you see this code, it's just starting a data segment. Okay, some contents are there within the data segment. Then I need you to observe the code segment. So code segment starts over here. There are some code written, right? Then the invocation of the factorial function, it happens over here, okay, using call fact. Then some other code is also here. So what you have to understand is, once the invocation of fact is done, then it, after the fact or that procedure returns, there are still things to be done over here. Okay, so ordinarily the control will return over here, then this will start executing. Okay, then what happens is, we should actually terminate the program. We should not allow the execution to get into the procedure. Okay, so what you have to do is, the part of the program that initializes all the registers or all the parameters for the procedure to work, right, that will be written first. Then the call to the procedure will be there. Then based on the result of the procedure, you may need to do certain other operations within the main part of the program. That too you can do. Immediately after that, what you have to do is, you have to write the code to initiate termination of the process. Then after this code, within the same code segment, you can write the body of the procedure. Okay, fact, proc, near, then on their body you can write. Okay, so the procedure ends over here, code segment will end over here, then the entire program ends over here. So what's the advantage? So advantage is after the invocation of this procedure, right, call, what happens is the control passes over here and that thing will be executed. Then what happens at the end of this part, right, especially over here when a return is encountered, what happens is we will go back to the line immediately after fact. So these lines will be executed, right, the pop part and other things will be executed. Now if this termination section was not there, what happens is the procedure body is the immediate thing. Okay, next, so ordinarily after execution of move bx ax, if these three lines were not there, what happens is the assembler goes into the procedure body, executes push bp and other sections of this procedure's code, and then it actually goes over to the end of the procedure, then it ends. So it actually means that we will be destroying the result that we obtained, okay, if the function is not properly placed. So just like I told, the assembly language level functions, right, they are actually not like high level programming language functions. That is, high level compilers or interpreters, they are much more intelligent. In case of assemblers, the positioning of code is critical as far as a programmer is concerned. So whenever you write a procedure, note that it has to be placed within the code segment in such a way that it executes only when you require, and there should be a proper termination event or a termination mechanism incorporated within your code segment, which will trigger whenever the entire operations that you require is done. Okay, so actually in the remaining section of this video we will discuss through the program, or we will go through the program. So I just wanted to show you the structure of the overall structure of the program, especially the positioning of the procedure, okay, which is critical when you write a program containing procedure. So this is a sample structure which can be followed for a typical code containing a procedure. Okay, you will have the data segment here with label storage. You will have the code segment. Alright, within the code segment, the initialization part for procedure invocation will be there. Then procedure invocation of the call part will be there. Then termination part of the entire function, entire code will be there, followed by procedure body. Note that the invocation should not be immediately followed by procedure body. Invocation and procedure body should be separated by a process termination or a branch. Okay, so after invocation, either a branch or a process termination should be taken so that the procedure body is skipped. Okay, so procedure body should only be entered from this call part. Okay, so it should not be a free flow after the call. After the call, either process termination or there should be provision to directly enter this code and this part, not the procedure body. Okay, so this is actually a critical area which we need to take care of. Note that only procedure body should be used from a procedure invocation, not as part of normal control flow. Okay, so it's initialization, invocation, termination part, then procedure body, or branch part and procedure body. So the purpose of this process termination or branch part is to skip the body and avoid unintentional execution. Now let's go through the code section by section and see how the stack varies or the content varies, and analyze how stack can be used to give parameters as well as take back the result. Okay, so the first section of the code is definition of data segment. Okay, so we are actually creating data segment over here, or the contents of data segment over here, and you can see here that the operand 5 is actually stored in a memory location which is labeled by num1, and we expect our result to be stored back to area num2, so initially we will define it as 0. Okay, and note that currently this is the stack's status, nothing is pushed into stack, so the base pointer is pointing to the first entry of the stack, which is currently empty. Okay, let's assume like this, and so is the stack pointer over here. Okay, so let's assume that the base pointer of this function is BP main, and it is pointing to an empty location. And now coming to the code segment, let's see what happens. Okay, so first AX is cleared, then the offset of num1 is loaded into BX, and from that offset, what is done? The content is transferred onto X. So you have to see what is num1. So we already know that num1 contains our operand 5. We need to calculate 5 factorial. So operand 5 is present in the memory address labeled as num1. So when we get the offset within the data segment and move the content to X, we are actually moving the value 5 to X. Now we are doing push AX. So when you do push AX, what happens is the content of AX with 5, right? AX along with its content 5, or the content of AX is pushed into stack. So this will be the stack status when the first push is executed. Now after that, we have to note that our operand is the content of AX and it has been pushed into stack, and now we are going to call the factorial function or procedure. So this is how we pass parameter to a procedure or function in assembly language programming. We actually push it into stack and call the procedure. Okay, all fact, what actually happens is we will branch from this point to the body of the factorial procedure. So this is the body of factorial procedure, further located downwards from this line of code, right? So this much line of code is going to be skipped. So the thing is, once you branch to a procedure, after completing the body of the procedure, okay, which happens over here, you have to return to a point from where the call was invoked. Okay, so the call was invoked from here, and actual expected execution should resume from here. So the address of this instruction, that is popx, right, which is a return address from the factorial procedure, should actually be preserved so that that can be used to come back to the remaining portion. Okay, so if we observe the current state of stack, the parameter AX has been pushed to stack for factorial function to process. So along with that, another thing to be pushed into stack is the return address from where the execution should resume once factorial procedure completes. So this return address is also pushed to stack. Okay, so this is effectively the stack frame of the main portion of our program. That is, the parameter along with the return address is present in the stack frame of the main portion. Okay, so you can see the state change. This was the first state of our stack frame. This is the second state of our stack frame. Now we are going into the factorial procedure. Note that when we are inside a procedure, we will create a new stack frame for the procedure so that its local changes can be limited to a particular area of the stack. Okay, so to above the stack frame, we will construct another stack frame for this procedure. So we are now inside the procedure factorial. As I told earlier, we need to construct a stack frame for this procedure exclusively. So there is a particular methodology to create a stack frame, new stack frame. So the methodology is first preserving the original base pointer. Okay, now creating a new base pointer. Okay, so base pointers actually define a stack or region of a stack, right? Or the region between base pointer and stack pointer is actually the working area of a stack. Okay, so first what we are going to do is we are going to push the current base pointer. So our current base pointer is BP main, or the base pointer pointing to the base of the stack frame of the main code, right? So this BP main is pushed into stack. So if you can see here, BP main is now pushed into stack. So stack was initially at this state, right, with return address at the top. Now BP main is at the top. So for our convenience, stack pointer is also shown from this point. Okay, so if you see our stack's condition now, BP main is currently pointing to base as usual. Now BP main is also at the top of stack, and top of stack is pointed to by the stack pointer. Now what we are doing is stack pointer is pointing to the preserved BP main. So we will make a new BP, okay, or we will make a BP for the newly created stack frame to point to this area. Okay, so that's what you can see here, BP fact. Okay, let's call the new base pointer or the new base of the stack frame that we are going to create as BP fact. So BP fact is made to point to the old preserved BP main or its location. Okay, the location of the older base pointer is actually the starting of BP fact, or BP fact or the new base pointer is now pointing to the location where older base pointer is residing. Okay, so from now on, whatever we build on top of the stack from point 4, it will be in a new stack frame. Okay, so that's the assumption. Now we will see what all things we are going to push apart from this. Okay, we are going to push bx and ax because it is assumed that bx and ax will undergo a change within this factorial function. Okay, so if you see point 5, bx and ax is pushed into stack, so sp will move, and bp fact, it is staying as it is. So you can see here that region between bp fact, that is newly created base pointer, as well as sp, okay, that is actually the new stack frame. So the new stack frame contains bx as well as ax. Now we know that our current stack frame is sitting on top of the stack frame of the main function, right? Now what we need this value 5 to be used within the factorial function. Okay, so we already know that bp fact is pointing to this area, and 2 words before, and if we move actually 2 locations beyond that, all right, or actually 4 bytes before that, we can get actually access to this one. Okay, so if we move 4 bytes beyond this bp fact, we will get access to 5. So that's what we are going to do here. Bp fact is now currently pointing to this location, so bp fact plus 2 will take us to this return address location, then plus 4 will take us to the location where the parameter 5 is stored. So from there we will move the parameter 5 to bx. Now our normal factorial computation will take place, and once the factorial computation is over, what we will do is we are now done with this parameter. So this parameter is no longer used for us, only the result is useful for us. So to this location, that is bp fact plus 4, we will move the result is actually 78h. So 78h is moved to this location. So that's what is done over here, that is ax will have the factorial computed, that result is moved to bp plus 4. Okay, so 78h will be moved to that location. Now we are done with computation of factorial, so we are done with the stack frame. So we are going to destroy this stack frame by popping out these values. Okay, so pop ax is done, pop bx is done, then we have to restore the bp main. So what we will do, we will pop bp also. So this bp main will be popped and will take up the location of bp fact. Okay, then return instruction is there. So what it will do is it will pop the return address and it will branch to that location. Okay, so we will branch to a location from where this factorial function was actually called. Okay, so once we branch, the stack frame will be like this, the result will be there, and the bottom of stack as well as stack pointer will be pointing to that result. Okay, so we will branch back. So this is the point where we are returning. So this is 7, right? At the point we are returning, what we are having is the stack pointer as well as base pointer will be pointing to the result. So when you pop ax, what happens is the result will be stored in x. Okay, now what we are doing, we are trying to access the offset to this memory location, and we are trying to move the result to that memory location, and then we are terminating the process. So this is how you will perform factorial or computation of factorial using functions and stack, or procedures and stack.